is really a trichotomy. True or false or meaningless. Being irrational says they do not exist integer a and b, so that a or b is equal to alpha. But this is a meaningless definition. And indeed, the generalized Collatz is, oh, by the way, now it's known that square root of 2 to the power of 2 is irrational, thanks to somebody called Gelfond and Schneider. It was one of Hilbert's problems. So there's another proof, and not this one, that is probably valid. You never know what they use. They could have used classical mathematics, so I'm not sure whether even their proof is valid, but let's hope that it is. So the generalized Collatz problem, this is due to John Conway, is indeed undecidable. Instead of taking the specific Collatz problem, which we don't know, it could be true, it could be false, it could be undecidable, meaningless in my terminology. There is no algorithm that inputs this type, a general rule. Instead of 2, we take n, and then exactly the same format, and outputs yes or no. And John Conway and others prove that this is undecidable. How do they do it? It's a usual trick. They say that this kind of problem is universal. If you can solve this problem, you can solve the problem about the halting problem of Turing. They reformulate it. They have a reduction like this. So this generalized Collatz problem is definitely undecidable. Probably the specific one is decidable, and it's probably right, but nobody knows. There is no rigorous proof today, but there is a non-rigorous heuristic proof that is very convincing. If you assume, and it's very likely that it's true, that the sequence, the orbit, is random, then in one step, in the even step, whenever it's even, it's basically 1/2. Whenever it's odd, it is 3/2. If you take the log of 2 is bigger. So you win. So it's like tossing a loaded coin with probability 1/2, no, not loaded, sorry, a fair coin. But with probability, if you have a head, you win log 3/2, log 1.5. And if you have tail, you lose log 2 to last. So of course, by the law of large numbers, eventually, there will be many, many more losing than winning. So eventually, you get less. And meaning, eventually, you get to a smaller integer. And again, the smaller integer. It's extremely unlikely that you're going to win, and only lose. It's like that stupid people go to a casino. In a casino, they have a cut. So you have 45% of winning, 55% of losing. So if you go only playing casino once, maybe, but if you keep playing all your life with probability 99.9999999%, you're gonna be a loser. So it's stupid to play in the casino. Same thing with the Collatz casino. You have it's math. So eventually you're gonna be losing. So that's your history. So many people tried. To be honest, most professional mathematicians took Erdos' advice and don't try to actually prove it. But lots of amateurs still send submissions to journals, and there's some people who specialize in finding mistakes in these proofs. But if you cannot prove something, if you try something and you fail, try again. Then generalize! No use being a damn fool and trying to prove your original conjecture. We have to make a living, and we have to try to find things that we can do. And often, the more general statement is easier to prove. If we are lucky, the general statement contains the original statement. And one good way to prove a difficult problem, for example, the Riemann hypothesis, is to prove the generalized Riemann hypothesis. The generalized Riemann hypothesis is much easier to prove, probably, than the Riemann hypothesis. The reason still nobody was able to prove even the generalized Riemann hypothesis is not generalized enough. You have to find even a super generalized Riemann hypothesis that will make it trivial or at least tractable. Unfortunately, there is no generalization of the Collatz problem that contains it. But we have analogs that are very similar sounding to the Collatz problem with the second order recurrence. So the Collatz problem is the first order recurrence. So here is something considered by two very smart mathematicians from the University of Rhode Island around 1995. Take any initial conditions, x of 0, x of 1. Then define x of n plus 1 to be the average of them if the sum is even. And define to be minus x of n minus 1 plus x of n if the sum is odd. This looks very much like Collatz. And it not obviously goes to a smaller number. Because, unlike Collatz, it could be negative or positive. So if x of n minus 1 happens to be negative, this is bigger. So it's not obvious that it's contracting all the time. So here are some examples. You take any arbitrary initial values. So Clark and Lewis experimented and did many examples. And they noticed that no matter where you start, sometimes it takes a long time, but no matter where you start, eventually, sooner or later, you get 1, 1, 1, 1, 1, 1, minus 1, minus 1, minus 1, and a little bit less more interesting, minus 1, 1, minus 2, 1, 3, 2, minus 1, minus 3. That's of length 6. So it all goes down to 3 possible cycles. The cycle of length 1, 1, of minus 1, and the cycle of length 6. And you can see, no matter how you start with a million and a billion, no matter if you iterate this mapping by hand or by computer, surprise, surprise, at the end, you get one of these 3 scenarios. So this exactly analogous to the Collatz problem that says eventually you get to the orbit 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. How to prove it? Just checking it on computer for billion of cases is not a proof. Now they had an ad hoc proof, but then came other mathematicians from University of Rhode Island, Jerry Ladas, Edward Grove, and the 2 graduate students, Amal Amle and Candace Kent. And they came with a beautiful human strategy, how to tackle this problem and many other problems similar to them. So in 1998, Amal Amle, Edward Grove, Candace Kent, and Jerry Ladas also generalized. They took a whole class of such mappings. And they considered all the 16 possible cases. The conventional wisdom, even today, is that computers cannot think. They can only compute. Computers can refute conjectures or check them for finitely many cases. So one way to get famous is to let your computer run and test the Goldbach conjecture for the first billion, zillion, zillion, zillion cases. And if you find 2 you